Okay, welcome back, and hope everybody had a good weekend. All right, so let's see where we're at. So, okay, so I graded your last couple assignments. So on Blackboard, you should have seen a grade for the homework chapter 3 and the elasticity homework. All right, and I sent you my solutions for those. So let me know if you have any questions on those assignments. But the grades are up, and you have my solutions. But overall, the students did pretty well on those. The assignment due today is the chapter 4, so just make sure you post that on Blackboard before the end of today. Homework chapter 4 due today. And then what I'd like to do today is we'll do the final piece of material, the final chapter before the midterm, which is chapter 5. And so we'll do that today. And then also I'm going to do a little review sessions of practice problems for the midterm, and we'll do that after we finish chapter 5. All right, so we'll do chapter 5. That'll complete the new material. That'll go on to the first midterm of the first exam, and then we'll do some practice problems, which will in the midterm, which will essentially cover a lot of the main topics from chapters 1 through 5. Okay, and then remember that next Monday, July 5th, is an observed holiday, which means we will not meet. The university is supposed to be closed that day, and so no meeting next week, July 5th, and we won't meet after tonight for 2 more weeks until July 12th. So it says meeting 5, but there is no meeting 5. I just kept it. But the next meeting will essentially be meeting 6, which is Monday, July 12th, and the 2 assignments that we're going to cover today, homework chapter 5, and the midterm, both of those are not due until July 12th. So you have 2 assignments to do, including the midterm, but you should have plenty of time because you have 2 weeks to do those assignments. Okay? All
Okay.
right. Yeah. Oh, question? No?
No question.
Okay. All right. If you do, go ahead and ask. Um, all right. So what are we gonna, so yeah, let's go ahead and get started on today's material. And the first thing I want to do is cover chapter 5. So let's cover chapter 5. Okay. If you go on Blackboard, you can open up the chapter 5 document here under chapter 5, and then you can also open up the homework chapter 5, which we'll get to a little bit later. And if you go to PowerPoint on Blackboard, you can open up the chapter 5 PowerPoint. And if you want to refer to the older version, which I'm going to use to show some of the definitions and graphs, I'll have that open as well. And then we'll get to the midterm stuff later. Okay, so again, this will be the final chapter that goes for the first section of the class that goes on the first midterm or the first exam. In this chapter, we're going to review and cover the production process and costs. So you might have learned some of these concepts in 500B or any Intro to Economics business course, but we'll cover some of the main things and go a little more in detail on how firms make decisions. All right, there's a video you can look at when you get a chance on revenue, profits, and price. All right, so the first thing we're going to cover is something called the production function. You might be familiar with this concept or simple model. And this shows how output is produced, and it's a function of the 2 basic inputs, which are capital and labor. Okay, so your production function is going to typically look like this, and this means output Q is some function, and that output is determined by different combinations or levels of capital K and labor L. So depending on the function, if you add more capital or you add more labor, you're going to get more production. Okay, so this is different combinations which can yield the firm more output by either adding more capital or adding more labor, both of which can increase production. Okay, and then also make a note. So normally we assume that kind of short run and long run periods in microeconomics, and so most of the like firm behavior and the profit maximizing and the interesting findings come in the short run period. And the short run is typically when capital is fixed and labor is variable. And so we're going to kind of assume that when we do these short run decisions that capital is fixed, and which means that firms can't really adjust their capital like uh, build more buildings or add more computers or any more infrastructure into the long run. But in the short run, they can change labor. They can hire more workers. They can fire workers. They can add more hours. They can change what they do with their labor force in the short run. But as you're probably familiar with, the capital stock is fixed or constant in the short run. It's not to the long run until the firm can change capital. Okay, so one thing we look at here is the marginal product. And the marginal product is the different or the value added from adding one more of each of the different types of the production process or each of the inputs, I guess you can call them. So, okay, so you probably learned from 500B, at least I think you did, that these simple definitions of total product, and that's just the total amount of output you produce, the average product, which is the average amount you produce given whatever output you're producing, right? Just total product divided by Q, and marginal product would be the change in output by changing one of the factors of production or adding more of it. Okay, so basically, if our production function takes this simple form, well, this one here, where output is a function of both capital and labor, and then you want to know on the margin what happens to output. So whatever particular point you're at in the production process, if you add one more unit of capital, what's the effect on output? And if you add one more unit of labor, what's the effect on output? So those are the marginal products, in particular, changing either of these things by one unit or adding one more of them, and what's the marginal change on output. Okay, so since we have two inputs, we have two different definitions for marginal product. There is a marginal product of capital, which looks, here's the notation, MP subscript K, the marginal product of capital. And you can see that that's when you change capital, what happens to output. Okay, so pretty simple there that when you're looking at what happens when you add one more unit of capital, what's the marginal effect on output? Okay, and you can do the same analysis or the same term for the labor input. So MPL or MP subscript L is the marginal product of labor, and that's when you change labor, what's the change or the resulting change in output? So if you change labor by one unit, you add one more hour worked or one more unit, whatever it's measured in. What's the resulting effect or change on output? Okay, so these definitions are simple, but they're very important when you're looking at how and where the firm should make decisions. So marginal products that apply to both capital and labor, simply just when you change the input by one unit, what's the resulting change in output? Okay, next thing is called the value marginal product. And so since we know that the marginal product is the change in output when you change one of the inputs by one unit, this puts a dollar value on those marginal changes. And so what is the value of each of those marginal products? So when you change an input by one unit or add one more of it, and you get a resulting change of adding more output, what's the value of that? And to do that, it's pretty simple. You just kind of multiply it by the price of the good, because that's how much, if you get this much more output and the value of that output in the market is the price, then the value of that change is how much that change is in dollar values, which is just multiplied by the price, right? Oh yeah. So before we talk about the value products some more, just make a note that this is typically it depends on what type of production process or good or service you're looking at, but typically your product or your production has different phases in the production process, and it typically looks like this. So if you look at this graph is really useful and explains a lot in the changing marginal returns. So if you look here on the y-axis, this is just the product, and down here this is labor. So basically, when you add more units of labor, what happens to output? So if you look at this main curve, the total product curve, this is just like a production function, right? So this is when we're only looking at labor and how that affects production. When you add more labor, you get more production. But what's the change on the margin? So you see that if you're at zero, okay, there's no output. Obviously, if you're looking uh, if you have no labor, you're going to get no production. Okay, so then when you add one unit of labor, you get a lot of production. Okay, because this first person or this first hour did a lot, so it went from zero to a lot of things, and then you add a second person, you get more production. You get a third person or a third hour. But depending on the production process, at some point in this case, this example, it's the fifth unit of labor where the marginal change. So in this whole first region, there's increasing returns. So each additional unit gives you more return than the previous unit. Now in this section, which starts from going from 5 to 6 units of labor, we now get decreasing marginal returns to labor, which means that you still get more output, but you get a lesser extent than you had before. And then at some point, in this case, it's point J, uh, there's not enough work or too much or not enough capital to be used with more labor, and so each additional labor decreases production and you get negative returns. So you kind of get three stages to the production process uh, in a typical production function, where first you get increasing returns, then you get increasing returns at a decreasing rate, which are decreasing marginal returns, and then you just get negative returns. All right, so you can put any, I guess, typical example to this concept, and it usually applies. Now the the number of units of labor for which the phases change depends on what you're producing. But let's say we're looking at like a pizzeria or a pizza restaurant. Okay, so if we have the restaurant and we have everything set up with the ovens and the ingredients, and there's no workers, right? We're gonna have no production. But if you put one worker in the kitchen, you're gonna get a bunch of pizza. You put two workers, all right, one worker can make the pizza, one worker can put it in the oven. You get a third worker, still productive. That third worker can, help make the pizzas, help make the ovens, take some orders, and there's plenty of work to go around. But maybe when you get to the fifth worker, there's still production process, right? There's still more pizzas produced, but less than there were before. And maybe when you get to the 10th worker, you put a 10th or 11th person in the kitchen. There's not much to do. In fact, they're probably, bumping into people or just like knocking things over. So if there's no work, then adding more people in excess of what can be done, like if there's no more work that can be done, if there's 10 or more people in the kitchen, then each additional worker or hour is going to give you less returns because they're actually being anti-productive, right? So that's kind of what the idea is. Okay, so if you take this graph and you think of any business you're interested in, I bet you can think of examples in which, at first your labor is really productive. The second stage is they're productive but not so much. In the third stage, you just have too many workers and you just can't use any more labor. There's no more work to be done. Okay, so we were about to talk about the value marginal product, which is the value to the firm of each um, change on the margin of the units of labor and the units of capital. All right, so nice simple definition. The value marginal product is the value of the output produced by the last unit of input. Okay, so this should make a ton of sense when you look at it, where if the MPL is the change in output by adding one more unit of labor, then the value to the firm of that change in output is the change times the price, right? So if you get this much more output, then each of those outputs is valued by the price on the market. And so this change times the price it's worth in the market is the value to that change. Okay? And that's called the VMPL, uh, or the value marginal product. Okay, same concept applies to changing capital if we're looking at long run decisions, where if you change capital by 1 unit, the MPK is the change in output, right? This is the marginal effect of changing 1 unit of capital on output. And that change in output multiplied by the price of the good on the market is the value to the firm of that change in output. Okay, so you get this resulting change in output, and each output is worth P, the price, and therefore the value to that change is this. So this we would call the value marginal product of capital, or the VMPK. Okay, so next thing is to look at how the firm would use this information, this theory, to try to make a profit maximizing choice of how much capital and or how much labor to use. Okay, and we're going to see that I mean, it's often hard to do this, in practice, but what the firm would want to do is see these conditions here. All right, if the value on the margin of the change in labor is the value marginal product that we just talked about, then the firm would be willing to pay up to the wage, right? So if they're getting this much value on the margin, then they'd be willing to pay that additional worker, that additional hour, this wage to get this much value. Okay, and the same thing applies for capital. It's a little more complicated because we're talking about the rental rate of capital. Okay, so remember we just talked about the value marginal product, which is the value to the firm of the change in output when you add one more unit of capital. And the firm would be willing to pay up to the rental rate of that capital. And the rental rate of capital, think of that if they don't own the capital, they'd be willing to uh, essentially rent or lease the capital, so lease the building or lease the computers at this rate, and therefore that's the value to the change in capital. So this is kind of the key term if you're assuming the firm doesn't own the capital, they're renting it, and even if they own it, you can think of the rental rate of capital as being kind of uh, interchangeable with the interest rate. And so the interest rate would be the cost of the firm to borrow money and make an investment. So in theory, in a perfect market, if everything works out, either the firm could borrow money at some interest rate and then buy the capital, or they could rent the capital, rent the building, rent the computers, whatever, at this rate. So in theory, if one of these was bigger or less than the other, then the firm would do the cheaper option. But in this case, let's assume that the firm is renting because it's equivalent to the firm taking out an investment at the interest rate at this rate, and so the firm would be willing to pay up to the rental rate of capital equal to the value of the capital by changing the capital by 1 unit. Okay, so this here's essentially the um, profit maximizing input usage. So you can apply this concept to both capital and or labor. So if you're looking at labor, like I tried to describe, the firm would be willing to, where the ideal condition is the firm would pay the unit of labor exactly equal to its value. So that's essentially saying like the unit of labor is this wage and the value is this VMPL. So if the change in labor is worth this much to the firm, then they'd be willing to pay this much in the wage, right? So it kind of equals out there. So that would essentially be the profit maximizing choice where the firm could pay the wage equal to the value marginal product depending on where the firm is in the production process. All right, and the same condition would apply to capital, like I showed here, where if the value to the next unit of capital is the VMBK, right, the change in capital, or sorry, the change in output resulting from the change in capital that multiplied by the price, which is the value of that change, then the firm would be willing to pay for that value equal to the rate it pays for that uh, input. Okay, so if this is the value of a change in capital, this is how much the firm would pay to use that extra unit of capital. Yeah. All right. So next thing, we're gonna look at some actual like numeric or algebraic forms that of different production functions, and see if we can apply some of the concepts we learned here. All right, everybody good so far? Okay. Okay. Uh, yeah. So there's three different types of numerical, or not numerical, but three different types of production functions that we're going to look at here. And so um, the simplest will be a linear production function. The next one will be this thing called the Leontief production function. I think that guy was French. And this is when you produce output only in fixed proportions. And the third one is a very popular and very useful production function with nice properties, which is called the Cobb-Douglas production function. Okay, so we know that our production function is defined by you add more, here's the function, you add more capital, or you add more labor, you get more output. Now, what does that function look like? It depends on what your firm or your production process look like. So let's look at some examples of what the production function could look like. Number one, it could be linear. So it could take the form like this, where output is a linear combination of capital and labor. Okay, so basically if you had this much capital, this would be the effect on, or the change on output. Or if you had this much labor, this would be the effect or the change on output. Okay, so output here is just a simple linear function where AK plus BL is some parameter-based linear function where output is a linear function of capital and labor, and therefore uh, capital and labor are essentially independent of each other. Okay, so we'll look at some examples there. Yeah, so for example, if A was 4 and B was 1, your production function could look like this, which is with the parameters, the numerical parameters, 4K plus L. So any estimated value for the parameters or the coefficients, A and B, and your production function could take some linear form where it's some A times K plus some B times L. Okay, this next one looks a little weird, but it's called the Leontief, and this is essentially a production function that assumes that inputs are used in fixed proportions. Okay, so it's essentially your production function is the minimum of one of these conditions. So it's the minimum of either BK or CL. So here's a case where your output can only be used if like this is uh, these ratios hold. So here, okay, yeah, actually this is the best way to do this is look at an example, and I have an example for this one that we'll do here, which is demonstration problem 5.1. Okay, so if you were to go to the chapter 5 section and open up the chapter 5 document, then that's what we're looking at here. Okay, so we got some optional videos, production functions, some more on the value marginal product, some more on, we haven't got to that yet, but we'll talk about the marginal rate of technical substitution. So here we go. First little example I want to go through here will help us explain the fixed proportions Leontief production types. So demonstration problem 5.1. So the engineers at Morris Industries obtained the following estimate of the firm's production function. How much output is produced when 2 units of labor and 5 units of capital are employed. So here's the production function. Uh, Q equals the minimum of 3K 4L. So that means that output is you only get more output when you have this combination, like uh, you know, 3 and 4, 6 and 8. So this ratio or these proportions have to be met, or else you won't get to the next unit of output. So you only get more when these exact ratios hold. So for example, if we had 2 units of labor and 5 units of capital, just plug those in to this function. So plug in the 5 here and the 4 here, and we get Q is a function of K, which is 5, and L, which is 2. So that's the minimum of 3 times 5 units of capital, comma, 4 times 2 units of labor. So Q equals the min of 3 times 5, which is 15, or 4 times 2, which is 8. So the way you take away this min function is pretty simple. So once you plug in your inputs, um, output is just the minimum of the two values. So the minimum, what's the lowest number between 15 and 8? It's obviously 8. So min of the lowest number, if there is one, in this case, the minimum of 15 or 8, output's 8. All right, so this is again a type of production function where output has to be in fixed proportions. Like if you have one computer and you can only put 2 people on the computer to get more output, then that's your your fixed proportions would be like K 2L. Okay, so if only this specific specified um, proportion work or gives you more output, then that's how this little production function would work. So you just plug in the numbers, and your output is just the min of whatever the two numbers are. Okay, so the next or the third type of production function is a very widely used one in microeconomics, which is called the Cobb-Douglas production function. So this one assumes some degree of substitutability, and it usually takes this form where Q is a function of K and L, but K is raised to the A and times L to the beta. So this is nonlinear because uh, output is now a nonlinear function of K and L, and it takes this form where K to some parameter A times L to some parameter B. So these parameters, A and B, determine the relationship between capital, labor, and output. Okay, and so we already did this, right? Demonstration problem 5.1. We learned about a little example of a Leontief with the fixed proportions. Okay, so we learned about three different types of production functions and what those might look like in the general form. Okay, and now we can apply the concept of marginal product, so the measure of productivity, to each of these general types. So essentially, if you're looking at it like calculus-wise or change-wise, then changing labor gives the resulting change in output, so that's the marginal product of labor. And if you were to do like uh, a simple derivative, like you would do in calculus, then essentially what I'm saying is that the partial derivative of output with respect to labor would be equivalent to the marginal product of labor. And the same would be applied to capital, is if you're looking at it calculus-wise, MPK, the marginal product of capital, is the partial derivative of output with respect to capital. So this is another way of saying, for this one, if you change labor by 1 unit, what's the effect on output? And this one, if you change capital by 1 unit, what's the effect on output? Without holding everything else constant. Okay, so in the text, so in this text or in the text, if you purchase the textbook, or you can just look at it here. If you're not up on your calculus, there's a formula for each of these. Sorry, question?
姐，我看着我去买那个什么国宝了。对，
Okay, so if you don't want to use calculus or you haven't freshed up on calculus, um, there's formulas for each of these um, marginal products. So here's the linear, right? Um, and so if this is the form where your linear production function we talked about is AK plus BL in the general form, then your MPK would be the derivative of this with respect to K, which is just A, right? And your MPL would be the derivative of this with respect to L, which is just B. Okay, so you can either look at it like taking the derivative of this with respect to first K, which gives you that, second L, which gives you that, or you can just look at the formula where you know that whatever number here, A or B, is going to be the MPK, is going to be that value, and the MPL is going to be that value. So if we looked at this one, so here's our example with numbers. Q is at 4K plus L. MPK would just be 4, right? And the MPL would just be 1. Okay, so in this case, A is 4, B is L. A is 4, B is 1. Okay, you can't really do this. You can't really evaluate the marginal product for the Leontief because it's got a weird property. And so don't worry about that one for marginal effect because the marginal effect depends on the ratios. All right, so there's not a direct, you can't really differentiate it with meaning, but you can do it for the other one. Okay, so again, for the linear, if you need to calculate the value marginal product, you can use the formula, or if you like taking the derivative or thinking about it with calculus, you can think about the MPK as dq dk, which is A, or dq dl, which is B. So it's going to get you the same way. Either use or memorize the formula, or just take a simple partial derivative if you're familiar with using calculus to do that. Okay, so for the Cobb-Douglas, the value products are a little more complicated because it's nonlinear, but it's not too bad. So remember, our general formula was for the Cobb-Douglas was Q equals K to the A, L raised to the B. This there. And then based on what those values are, you can take the value marginal product of that. Um, so again, here's the formula. You can use the formula and just plug in the numbers, which would be MPL equals B times K raised to the A times L raised to the B minus 1. Or MPK is AK raised to the A minus 1 times L raised to the B. Or a way I like to do this is just to take the partial derivative. So the calculus alternative, either just use the formula or take the partial derivative. So when you're looking at this function, k to the A, L to the B, you can take a simple partial derivative with respect to both of the inputs. So the MPK is equivalent to the partial derivative of that function with respect to k. And remember, this is the exponent. So this is like, um, x squared or x raised to the 3 or x raised to the 1/2. So a derivative, to calculate it, just take the exponent down and subtract 1 from the exponent. So this is the exponent. It comes down here, and then you subtract 1 from it. So A minus 1, and remember that's a partial. So this part is the L part is constant in a partial derivative with respect to K. All right, so see how the partial derivative of that with respect to K, just bring the exponent down, subtract 1 from it, and then this part is constant because that has to do with labor, not capital. Okay, same deal for the MPL. You could alternatively differentiate the function with respect to labor. So dq, dl, okay, take the exponent for labor down, which is b, subtract 1 from it, b minus 1, and then this part is constant because we're only taking a partial derivative with respect to labor. Okay, so the MPK becomes a times k raised to the a minus 1 times l raised to the b, and the MPL becomes b times k to the a, l raised to the b minus 1. Okay, so it's your choice here, but when we do when we do problems and examples, either just stick with the formula and plug in your numbers, or if you're familiar with doing it this way, just go ahead and take a simple partial derivative of each input with respect uh, of the production function with respect to the input. Okay, so should we look at a demonstration problem where we're using this concept I just tried to explain? Um, let's do that. So this is a nice one on page 140. Well, I have this prepared. I have this solved in the Word document. Okay, demonstration problem 5.2. A firm produces output that can be sold at a price of $10. The production function is a Cobb-Douglas below. If capital is fixed at 1 unit in the short run, right? So in the short run, capital is not going to change. The question is how much labor should the firm employ to maximize profits if the wage rate is $2? So we got a lot of information, but we could break this problem down and solve it using the concepts we've learned um, for the firm to maximize profit. So here's our um, function. K raised to the 1/2, L raised to the 1/2. So this is basically like this is A and this is B. So this is the actual function, K raised to the 1/2 times L raised to the 1/2. And we know that capital is fixed, but the best case for the firm to maximize profit would be to pay the wage or produce output at the point when the VMPL equals the wage rate, right? So we learned that if this is the value of the margin, then the best case is for the firm to pay that wage on the margin. So when this condition holds, that's the best uh, level of output for the firm to produce if it wishes to maximize profit. Okay, so we're trying to find this condition, and we have everything we need here. So first, um, the problem said that capital is fixed at 1 in the short run, so just plug in 1 there for capital, and we get 1 raised to the 1/2 times L to the 1/2. 1 raised to the 1/2 is just 1, so the production function simplifies to 1, I'm sorry, to L to the 1/2. So when capital is fixed, this is our simplified production function in the short run. Okay, now let's calculate the MPL. So the MPL is the partial derivative of output with respect to labor. So do that, or either you can use the formula from the textbook, but you would get 1/2 times L raised to 1/2 minus 1, and 1/2 minus 1 is minus 1/2. So this is the full MPL. 1/2 L raised to the negative 1/2. Okay, so now we got part of this done, but we're looking for when the VMPL equals the wage. So we got the MPL. What's the VMPL? That is defined as the price times the MPL. So it's the value to the firm of changing labor by 1 unit, which is exactly the price times the MPL. Okay, so we got this, right? Let's just plug in P, which is it was given at 10. So the VMPL is price, which was 10, times the MPL, which we just calculated, 1/2 L to the negative 1/2. And then simplify, 10 times 1/2 is 5. And so the VMPL simplifies to 5 times L to the negative 1/2. All right, so now we got the VMPL. All we need to do now is find the condition where the VMPL equals the wage, and that's the output this firm wants. So let's find this condition. We just got the VMPL, which is 5 times L to the negative 1/2, and we know the wage is 2. Okay, that was given. So here's the condition we're looking for, and let's find the amount of labor that satisfies this condition. So it's gonna take a little algebra, but we're trying to find when what labor is when this condition holds. All right, so when does 5L to the negative 1/2 equal 2? Divide both sides by 5. We get L to the negative 1/2 equals 2/5. If you raise both sides to the negative 2, okay, this part would cancel out as 1, and you get L equals 2/5 to the negative 2. 2/5 to the negative 2 is equivalent to 5 squared over 2 squared, which is 25 divided by 4. And finally, when you work out all this algebra, it comes out to the optimal L. The optimal amount of labor would be 6.25 units of labor. So that's how much labor we would want to satisfy this condition, which would maximize profit. Okay? Um, yeah, so there's definitely at least one homework question, and I think an exam question on this type of problem. So questions here on what we did here for this to solve this one? Okay. So thus far we've only talked about production, and now we need to talk about costs, the firm's cost. So isoquants are how much it costs the firm to produce a certain amount of output. Okay, so isoquant, it's a weird word, is defines the combinations of inputs that yield the same level of output. So see, it's kind of similar to what we learned last time with the difference curves, where we had good y and good x. So look at it the same way, where this is capital and this is labor, and each point on this curve gives the firm the same level of output. So we could use any of these combinations to get Q0, or any of these combinations to get Q1. So if we're going outwards from the origin to the right, that's more output. But any point on a given isoquant yields the same level of output. So any point on this black curve is 100 units of output. Any point on this pink curve is 200 units of output. Any point on this red curve is 300. So to produce more output, you got to get to a higher isoquant. But on a given isoquant, different combinations can be substituted of capital and labor to get the same output. Okay, now oh yeah, so sorry, there's the isoquant would look different depending on the type of production function. So this one would show a nice example of the Cobb-Douglas situation. where we have some degree of substitutability. So basically, like if you get to more extremes, your capital becomes less useful, right? So if you're using a ton of capital, or I guess that would be a ton of labor. No, a ton of capital. So if you're using a ton of capital, just using a little more labor would give you a lot more output, and vice versa. So when you're somewhere in the middle, the trade-off between capital and labor to get the same output is somewhat similar. But when you're on the extremes, you're using a ton of labor, then you can give up a bunch of labor and just some capital to get the same output, and vice versa. So these would represent different examples of Cobb-Douglas isoquants. These would represent the other two types. So this is linear, right? So this is capital and this is labor. And see how the function is a linear combination of capital and labor. So anything on this fixed ratio would give Q0. Anything on this fixed ratio would give Q1, and so on. And the Leontief, the fixed proportions look like this because this assumes only fixed proportions yield the next level of output. Okay, so because you can only use output in this ratio, Q0 is only achieved at this point, and so if you're here and you use a bunch more labor, nothing's going to happen unless you add the specific change in capital as well. So you have to use the exact ratio or amount of both specified types to get to the next Q1 or Q2. And the output choice is just, so you're here, you're here, you're here, and using more of the other input without the predetermined ratio gets you nowhere. It's only when you use more in the fixed proportion aspects that you get to a higher level of output or to a higher isoquant. Okay, all right, big word here. The marginal rate of technical substitution, or the MRTS, shows the graphical and quantitative point in which the firm would want, or which, sorry, it shows essentially the slope of the isoquant. So the MRTS, or the marginal rate of technical substitution, is the rate in which the firm can trade capital for labor, or labor for capital, and be at the same level of output, or be in the same, essentially the same isoquant. So you can measure it as the MPL divided by the MPK, and you can also look at it graphically. All right, so it should make sense that the slope of the curve is the rate of trade-off. All right, so this one is a Cobb-Douglas production function, right, where we're at Q0 equals 100. So see what the MRTS is. It's pretty simple if you look at the graph, where if you want to remain this on the same output, you can be at point D. So if you want to give up some capital and produce and use some more labor and give up and be on the same level of production, you'd have to give up from point D to C, give up 3 capitals, and use 1 more labor, and you're on the same curve. So the rate of trade-off is 3 to 1 there. Or if you're at point C, to go along the curve, you can give up 2 capitals, add 1 labor, and be at point B. And here it's 1 to 1. So see how it gets, the farther you get up here, the more capital you have to give up to get to the same point on the same or not the same point, but the same level of production. And the more you get over here to this extreme, then the more labor you have to give up to be on the same production level. So see how the rate of trade-off changes? But the rate of trade-off, or the MRTS, the marginal rate of technical substitution, is always how much capital you have to give up to use more labor, or how much labor you have to give up to use more capital and be on the same isoquant. Okay, so the slope of the curve is always the change in labor resulting on a change in capital, or change in capital over the change in labor, or the MRTS, and that slope changes depending on what point you are on the curve. All right, so again, the marginal rate of technical substitution, trading K for L, is the change in the the change in output by changing labor divided by the change in capital, the change in output by changing capital, or the MPL divided by the MPK. So the marginal products essentially define the rate of trade-off, trading capital for labor to be in the same isoquant or produce the same amount of output. Okay, iso costs. All right, another fancy word. Okay, so yeah, this is kind of similar to the budget line for the consumer, where we define W as the wage rate, L is how much labor, and R is the rental rate of capital, how much it costs to use a unit of capital. So if we use this much labor at this price and this much capital at this price, then the total cost to the firm is this times this plus this times this, right? So if you use this much labor, it costs this much, so that's the cost of labor, and add the cost of capital, each unit costs that much, and then the total cost of labor plus capital is big C, which is the total cost of the firm of using different combinations of capital and labor based on the rates which you have to pay those units. Okay, so C cost is WL plus RK. We just talked about that. And you can put this ISO cost line on the same KL graph. Uh, so this is K, this is L, and what you want to do, just like we did with the budget line, is you want to graph it or to see the intercepts essentially and the slope. You want to solve this function for K as a function of everything else. So if you take this equation 5-1, subtract WL from both sides, and divide by R, you would get, okay, so see, here's the first step. Uh, divide by R first here. That was what they did first. So divide this by R, you get W over R times L plus K equals C over R. And then just subtract W over R times L from both sides, and you get K equals C over R minus W over R times L. And you can see that the intercept when labor is 0 is C over R. And if you did the other way, the intercept when K is 0 would be C over W. So the intercepts are determined by the total cost the firm has to spend and the price of each unit of that, right? The price of capital or the price of labor, depending on which intercept you're looking at. And then you can clearly see that the slope, or the ratio at which uh, capital and labor can be substituted to get the same level of costs depends on the ratio of the wages. So the ratio of the wage rate to the rental rate of capital determines the trade-off rate to cost the same amount. Right? So if the wage rate goes up, labor becomes more expensive, and you'd probably use some more capital. Or if the rental rate of capital goes up, capital gets more expensive, and you probably use some more labor. All right, so the slope of the curve, negative W over R, exactly determines the slope of the curve and how much the trade-off is for capital and labor to get to the same level of cost. Okay, now we're going to kind of bring everything together and show how the firm can minimize cost or maximize profit. It's essentially the same thing. Um, by it's similar to what we looked at, or graphically, it's similar to what we looked at with the difference curve and the budget line, where we're looking at the point where we're trying to get to the most production possible given to how much the firm wants to spend. So you can just think of it as the consumer was trying to get as much satisfaction as possible given their budget, while the firm is trying to produce as much output as possible given the costs they have. So they're trying to spend this much and produce as much as they can. And that's going to exactly be the graphical point when the rate of trade-off equals the ratio of the wages. So when the MRTS equals W divided by L, it should make sense when you look at it on the graph. That's the optimal point in which if the firm wants to spend this much, that's how much capital and labor they should use. Okay, so we're bringing those two concepts together on the same, here, this is K, this is L. So this is how much capital the firm uses from zero to whatever, and this is how much labor they use from zero to whatever. And these are different cost structures, and the ISO quants are different output achievements. So see how if the firm is going to spend this much C2, then they can produce the maximum amount of output they can produce is at point B, where that ISO quant is tangent to the ISO cost line. Okay, so if they're going to spend C2, um, they could produce any combination under it, but this is the farthest they can get to output wise, and this would be the best point given the fact that they want to spend C2. Now, if they're able to spend C1, they could get to a higher production level. But see how we kind of put the, let me see if there's a graph that shows, no. All right, so let me bring these two things together. All right, so the slope of the ISO quant we talked about was the negative MRTS, right? The rate of trade-off, getting the same level of output. So the slope of the ISO quant is the MRTS, and the slope of the ISO cost line is negative W over R. And now if those two things are tangent, that's got to mean the slopes are equal, which would mean that W over R has to equal the MRTS, which is exactly the point here. So at that point B, uh, the MRTS equals the ratio of the prices, W over R, and that's the point, assuming nothing changes, the firm would use to minimize costs or maximize production. They would use this much, B would be this much capital, and this much labor would be the best option to spend this much. And now if the wages change or the budget of the firm changes, we'd have to reevaluate, but given these wage rates and this rental rate of capital and this cost the firm wants to spend and this um, Cobb-Douglas function, point B is the optimal amount of using K and L to minimize cost. Okay, so this condition I've highlighted here, that holds exactly where I showed you on the graph with the MRTS equals W divided by R, or the rate of trade-off equals the ratio of what you got to pay those inputs. Okay, so we're gonna look at some more examples in a minute here. Um, okay, so the last couple of slides you can ignore here. We're not going to do that, so don't worry about slide 15 or 16. That's the math there goes beyond what I want to do here. So we've done everything I want to cover in the PowerPoint. Okay, so we left off here. We're determining that the cost minimizing option is to choose capital and labor at which satisfies this condition. All right, so let's look at some examples. Okay, so on the chapter 5 Word document, I have some other examples or demonstration problems from chapter 5 that I solved that we can go through to learn some more concepts here. So I think there's three more. Yeah. So demonstration problem 5.3. So temporary services TS uses 4 word processors and 2 typewriters to produce reports. The marginal product of a typewriter is 50 pages per day, and the marginal product of a word processor is 500 pages per day. The rental price of a typewriter is $1 per day, whereas the rental price of a word processor is $50 per day. Is TS temporary solutions utilizing typewriters and word processors in a cost minimizing manner? So we'll apply the same concept for labor and capital, where here we have two inputs, um, word processors and typewriters. So remember, the cost minimizing input rule was where the uh, MRTS equals W over R, or if you multiply across, that, okay, so here was the condition, the MRTS equals W over R, but we know the MRTS is the MPL over the MPK. All right, so then the MRTS becomes this, and if you just cross multiply, you can see that the firm wants to pay on the margin up to they're trying to pay the value of the input up to the rate they have to pay to use it. So we get a nice condition where the MPL over the wage rate equals the MPK over the rate of capital. So we want to use labor up to the point when the MPL is equal to the wage rate or the ratio, and we want to use capital to the point when the MPK divided by R is that. So we want to trade off capital for labor up to the point where their values are equal. Now, if one of those values changes or the wage rate changes, then this will change. But the cost minimizing solution is going to be when the MPL over the wage rate equals the MPK over R, which is another way of writing this. Okay, so let's use this concept to do this problem we're about, the demonstration problem. So normally the MPL divided by W would be equal to the MPK for R if we're looking at capital and labor. But instead we're using word processors and typewriters. So let's just assume that one of these things is for word processors and the other input is for typewriters. So we want, using the same concept, we want the marginal product of word processors divided by the price of word processors to be equal to the marginal product of typewriters divided by the price we have to pay for typewriters. Okay? Now, if that doesn't hold, then we're using one of the inputs inefficiently. Okay, so start with this general formula, and let's plug in the information given here in demonstration problem 5.3. So let's see. Word processors put 500 pages per day. Okay, that's the marginal product. Um, word processors cost $50 per day. So we're getting 500 pages per day at a cost of $50 per day for word processors, whereas for typewriters, the marginal product, 50 pages per day, and the cost is $50 per day. Okay, so we get 500 pages per day divided by $50 per day. Is that equal to 50 pages per day divided by $1 per day? So what's the cost per page? So if we divide 500 by 50, we know that word processors are giving us 10 pages per dollar, right? Divide that by that, we get 10 pages per dollar. And we divide 50 by 1, we get 50 pages per dollar. So clearly, we're getting more bang for our buck for typewriters. Yeah? And this is costing us 10, we're only getting 10 pages per dollar here. This is giving us 5 times as much, so we're definitely not using word processors and typewriters at the most efficient position because this is giving us more value than this. So we need to use more typewriters. So the marginal product per dollar spent on typewriters exceeds that spent on word processors. So word processors are 10 times more productive than typewriters, but we saw that they're 50 times more expensive. So the firm should make a change. They're not minimizing costs, and thus they should use fewer word processors and more typewriters up to the point in which this condition holds. And that would show you that this doesn't hold. In fact, this is higher than this, and so we should use more of this until these two are equal. Okay, so that's a nice example of showing that if you find that your marginal products or your cost minimizing input rule isn't holding, then that must be that you're not using enough of the more efficient one. You should use more of that until this condition is equalized. Okay, next one. Okay, so demonstration problem 5.4. So Acme Coal paid $5,000 to lease a rail car from the Reading Railroad, and under the terms of the lease, 1,000 of this payment is refundable if the rail car is returned within 2 days of signing the lease. So number one, upon signing the lease and paying $5,000, how large are Acme's fixed and sunk costs? And then 1 day after signing the lease, Acme realized that it had no use for the rail car. A farmer has a bumper crop of corn and has offered to sublease the rail car from Acme at a price of $4,500. Should Acme accept the farmer's offer? So there's two things. First, what are the fixed and the sunk costs given the conditions of the agreement? So in one, Acme's fixed costs are $5,000, so it spent that to regardless of how much output they produced. And then the sunk costs depend on how long they use it. So according to the agreement, for the first 2 days, its sunk costs are 4,000. They can get a refund there. After 2 days, if they don't take it back, they lose the entire 5,000, and that becomes a sunk cost. So it's important to see that the fixed costs are what you pay regardless of output, and the sunk costs are what you cannot recover. And then two, if they don't need the rail car, and this other farmer offers to lease it from them for 4,500, should they do it? And so obviously yes, they should sublease the rail car. So they're gonna, if they don't need it, they're already taking a loss here, but they're minimizing losses. And so see that Acme's total loss is $500 if it accepts the farmer's offer. So basically, they paid 5,000, but the farmer gives them 4,500, so they only lose 500. But if it doesn't accept the offer and they don't need the rail car, their losses will equal 4,000, and that's only if they return to the next business day. So you can see that there's a side deal that they should make, where if they don't need it, they can minimize losses. They lost the 5,000 if they don't return it in a couple days, but they can recoup 4,500 by subleasing it, and then only lose $500. Okay, one more example. This is just a review of um, marginal cost, variable cost, fixed cost. All right. So the cost function for managerial enterprises is the cost is a function of 20 plus 3q squared. So 20 is the fixed cost, and 3q squared is the variable cost because this depends on output. This does not. And determine the marginal cost, average fixed cost, average variable cost, and average total cost when Q equals 10. So this is just a nice quick review of those definitions. So marginal cost is the change in cost when you change output by 1 unit, or the partial derivative of cost with respect to output. And if this is our cost function, if you differentiate that with respect to Q, it's just 2 times 3, which is 6, times Q to the 2 minus 1. So it's 6Q is the marginal cost. And the marginal cost when Q equals 10 is MC10 is 6 times 10, which is 60. Okay, the average variable cost, we know by definition, which is variable cost divided by Q. So the variable cost on average. And take the variable cost 3Q squared and divide it by Q. And the variable cost just becomes 3Q squared divided by Q, which is 3Q. All right, the Q's cancel out there. And the average variable cost when Q is 10, 3 times 10 is 30. Okay, then you can see that fixed cost is just the 20. All right, so what's average fixed cost? Fixed cost on average. Fixed cost divided by Q. And fixed cost of 20 divided by Q is, that means our average fixed cost is always 20 divided by Q. But when Q is 10, then AFC 10 is 20 divided by 10, $2. Finally, what is average total cost? So total cost on average is just total cost divided by Q. So this divided by Q, 20 plus 3Q squared divided by Q, and we get 20 divided by Q plus 3Q. All right, that Q cancels out, and we get average total cost when Q is 10 is 20 divided by 10 plus 3 times 10. And simplify, we get 2 plus 30, which is $32. So you can, and then you can also see that you could also have done the average total cost by adding the variable costs plus the average fixed cost would also give you 30 plus 2, which is 32. Okay, so last couple were just some review of fixed cost, sunk cost, and then marginal cost, variable cost. Okay, questions on any of these examples here? Okay, so last thing for chapter 5, all right, we still got a bunch of stuff to do for the midterm, but the homework for chapter 5 is here. And again, this isn't due for 2 weeks because we don't have class next week. Okay, but if you open up the chapter 5 homework, you just got a couple questions. Number 1 is one on the Leontief or the fixed proportions example. So you got this specific production function, and the question is how much output is produced when 100 units of labor and 100 units of capital are employed. So you can use that example and just what we talked about for the Leontiefs to do that one. And number 2 is you got a production function. Um, okay, so a firm produces output that can be sold at a price of $1. The production function is given by this specific formula where it's 1k squared plus 4l squared. So all you gotta do is find the condition like we did in the example where the wage equals the VMPL. So the function's a little weird, but just follow that example and find the condition where the like we did in the demonstration problem where the wage rate equals the value marginal product of labor and solve for L at that point, and that's your answer to this one. Okay? All right, so 2 questions here for the chapter 5 homework. Shouldn't take you too long, but any questions on what I want you to do here for this assignment? Okay, so we are done with chapter 5, but I want to go over some practice problems and make sure everybody is good on solving the take-home midterm, which is also due in 2 weeks. And so you have 2 weeks to do these 2 assignments, including the midterm. Again, because next Monday is an observed holiday, we will not meet, so we won't meet for 2 weeks. And that's when chapter 5 homework and also the midterm exam will be due. So let's go ahead and talk about the midterm. All right, so you have some resources and actually the midterm. So if you go to on Blackboard, if you go to the midterm summer 2021 section, you'll see I have a practice midterm and some stuff, and then the actual midterm. Let's go over the practice midterm and its solutions, and then if you have any questions, please ask them. And then this is your actual take-home midterm, which is due in 2 weeks via email. But let's go over some practice problems, and this consider this kind of a quick review session for the exam. All right, so just there's PDF and a Word document. They're both the same thing. So here's the practice midterm. Uh, okay, so you have 4 questions. First one will be a net present value. All right. Second one will be you're gonna have a little sample piece of data. You're gonna run a regression and then interpret the elasticity like you did in the last assignment. Third one is like the chapter 4 homework where you'll do some budget line analysis. And number 4, the last one, is from the chapter 5 homework where we'll decide the profit maximizing amount of labor given the production function and the rest of the information. So 4 questions similar to this. And let's go over these questions to prepare you for the actual exam. Okay, where are we? All right, so here, let's open up this one under the practice midterm and solutions. We can open up the practice midterm solutions Word document and go through this as a review of the material. Okay, so number one, here's the practice exam. So number one will be a net present value, similar to what you did in the chapter 1 homework. So number one, a DJ disc jockey is contemplating the purchase of a new turntable that will cost $1,000 and has a useful life of 5 years. The turntable will yield year-end revenues of these amount. So 500 year one, then 300 year two, 100, 100, 100 in years 3, 4, and 5, and then that's it for the income stream. So use um, just the general definition, the general calculation for net present value, which is the discounted future value of all the payments minus the initial investment cost. So part A, what is the net present value of the turntable if the interest rate is 5%? All right, so sum up all the future values, discount them, sum those up, and then subtract the initial investment cost. So in the first year, we get $500, and that's divided by 1 plus the interest rate. So 1 plus 5%, 1 plus 0.05 is 1.05. And in the first period, or the first year, it's just raised to the 1. In the second period, we have to wait two years. So the $300 is divided by 1.05 squared, all right, because it's discounted squared. The interest could have compounded for 2 years. In the third year, it's 100 divided by 1.05 to the third. That's the third year's discounted um, revenue. Year 4, it's 100 divided by 1.05 to the 4. Year 5, you get 100 and the discounted value is 100 divided by 1.05 to the 5. So this is what you get for year 1, year 2, year 3, year 4, and year 5, and those are all discounted based on how long you have to wait. Add all these together, and then subtract the initial cost of 1,000, and you should get something like this. Minus that is something like negative $4.69, or about negative $5. And so it was close, but given the outcome, uh, the turntable wasn't worth the investment, and so the DJ shouldn't purchase the turntable because the net return on the investment was calculated to be negative, in this case, negative $5. So all of this didn't give us enough to cover the cost of buying it for $1,000. Okay? All right. Number two, you're going to get, or you have a simple Excel file that you're going to run a regression just like you did with the elasticity homework and answer some questions. So number 2, here's the sample file Q2. So for the practice midterm, this is the data if you want to practice with it. Okay, so see, you got your natural log of quantity, your natural log of price, your natural log of income, and there's about 49 observations of each. So you'd use that information to run a regression just like you did for your last assignment. Okay, so for your exam, take the sample Excel file, use that data, run a simple regression, and interpret the elasticities just like you did last week. Okay, so I took this sample information, and the problem said to estimate the following log linear regression, where natural log is a function of the natural log of price, the natural log of income, and you have to interpret the results here. So part A here, and on your side, your exam is going to be include a screen cap of your regression results, just like you did in the last assignment. So you'll take the sample data, you'll run the regression, and just in your answer sheet, throw in a screen cap like this. All right, so if you want to, I put under practice midterm solutions. Here is the practice midterm solutions Excel file. Okay, so here was the data, and then here is a sample of the regression I got, or the summary output. Just go in data analysis and use this data to get this. Okay, you did that last week. And the question is, you're going to take the screen cap and interpret the results like you did in your last assignment. Okay, so here we go. So part A is include a screen cap, so there's that. Part B is you're going to write out the equation using the estimated coefficients. So these are the coefficients for the intercept, natural log of price, and natural log of income. So our formula becomes, with the coefficients, LNQ equals 1.5096 minus 0.1690 times LNP plus 0.0400 times LNI. All right, so that's the equation with the coefficients. Part C, interpret the adjusted R squared. So we get an adjusted R squared of about 0.9996. And that would mean that approximately 99.99, almost 100%, 99.96% of the variation in LNQ is explained here in this log linear regression. Then you want to see if the coefficients are significant by looking at the associated t-values. This one for LNP and that one for LNI, and you can see they're both way bigger than 2 in absolute value, so they're both significant. And then part E is you're going to want to interpret the coefficients by using those 3 pieces of information that we talked about before. What type of elasticity is it? Is it inelastic or elastic? And what's the numerical interpretation? So for LNP, there's the coefficient, and for LNI, there's the coefficient. And what do those coefficients mean? So for this one, for LNP, okay, number one, it's the own price elasticity, right? This is the effect of a percent change in price and how that affects the percent change in demand. So the natural log coefficient for price is always the own price elasticity. It's definitely inelastic because this coefficient is less than 1 in absolute value. And then what is this? This is the percent effect on demand when price changes by 1%. Okay, so we did this before, but if price increases by 1%, then the resulting change on demand, then quantity demanded decreases by the coefficient 0.1690%. Okay, then this one, so for your last elasticity homework, make sure you check my solutions for this part because some of you didn't um, make the appropriate interpretation for the income one. So if it's the ln income, it has nothing to do with price. This has to do with income and demand. So lni, that coefficient is the income elasticity, right? And this is less than 1 in absolute value, so it's inelastic. And make a note here that this is probably the one that most students missed a point or two on the last assignment. And so this has to do with income and demand, not price. So here, this is the effect, this is the percent change on demand when you change income by 1 unit, which in this case is 1%. So if income increases by 1%, then quantity demanded increases by the coefficient, which is 0.04%. All right, so just make sure that when you're looking at this one, this is the effect, the percent effect of price on demand. And if you're looking at this one, this is income, and this is when you change income by 1%, what's the effect on demand? So make sure that this one is interpreted as income affecting demand, whereas this one was interpreted as price affecting demand, and there's a clear distinction there. All right, and then number 3, we've got a budget line analysis question. So let's suppose you have a budget of 120, and to maximize utility, you decide to spend all of your income on whiskey and pancake mix, all right? And the price of whiskey is $40 per bottle, and the price of pancake mix is $10 per box. And so remember, here's the general form. So this one should be very similar to the chapter 4 homework, which you're turning in by today. So the price of good X plus the price of good Y times Y equals your income. So start with that and just pick one good for X and one good for Y. And I picked X is whiskey, Y is pancakes, which means that PX is the price of whiskey and PY is the price of pancakes. And plug in the price of whiskey here for PX, which is 40. Plug in the price of pancakes here, which is 10. And plug in the income, which is 20. So this general form for this example becomes 40X plus 10Y equals 120. So this is our budget line for this problem. Okay, and then part A is construct a table showing the alternative combinations of the two products that are available to exhaust our income. So these different combinations would all equal 120. 3 bottles of whiskey and no pancake mix. That'll give us 120. 2 bottles of whiskey and 4 boxes of pancake mix. That'll give us 120. 1 bottle of whiskey and 8 boxes of pancake mix will give us 120. And also you can just buy pancake mix, no whiskey, which is no whiskey, 12 boxes of pancake mix, 120. So all of these possible combinations would give us whole numbers and let us use our full income budget of 120. All right, and part B is plot the data as a budget line in a graph. And what's the slope of the budget line? What's the opportunity cost of more whiskey and of more pancakes? So we know that the slope of the budget line is always the negative of the price ratio. So you can just take negative PX over PY and plug in the prices for this example. Negative PX is 40, PY is 10, and 40 divided by 10 gives us negative 4. So the slope of the budget line is negative 4. Okay. Uh, what's the opportunity cost of one more bottle of whiskey? Each time you buy a bottle of whiskey, you give up 4 pancakes, right? So plus 1 minus 4, plus 1 minus 4. So 1 bottle of whiskey is equivalent with an opportunity cost of negative 4 boxes of pancake mix. And flip it around for pancakes. Every time you buy 4 boxes of pancakes, you give up 1 bottle of whiskey. So 4 boxes of pancake mix, you're giving up 1 bottle of whiskey. And if you divide by 4, that means that 1 box of pancake mix is equivalent to giving up a 4th bottle of whiskey. All right, and then here's our budget line where this is how much, this is buying pancake mix, this is buying whiskey, and these are the combinations. So essentially I just plotted these points, 3 and 0, 2 and 4, 1 and 8, 0 and 12, and that's our initial budget line here, like that. Part C. Uh, as a result of the government stimulus payments, suppose your budget increased to 400, and then show the new budget line for Part C in the diagram. So here, we're essentially getting a boost of income. And so you can see this, I did this in Excel with the, okay, so here's the initial graph. And then here we got, our income went from 120 to 400. So you can see that the prices are the same. So the new budget line is 40 times X plus 10 times Y, which now equals our income of 400. So what different combinations of X and Y give us 400? All of these here. All right, so you can plot all those points. You can see you can now buy more whiskey, more pancake mix, or more of both. And this intercept becomes 10 and 0. And the other intercept becomes 40 and 0. And this is our new budget line, where you can buy up to 40 boxes of pancake mix, up to 10 bottles of whiskey, or any of these points in between. So this just plots all those points. Okay, so you can either do this in Excel, or you can do this on graphing paper, whatever's the best way for you to do it. Okay, and then finally, part D, suppose the price of a box of pancake mix increased to $20. Now draw the new budget line, but the income is still 400. So we had a couple changes. So first, income went up. Now, the price of pancakes went up to $20. So the budget line is going to kink in because now pancakes are more expensive. All right, so see that? So now the budget line with the $400 of income is the new price. Sorry, the price of whiskey is the same, 40, but pancake mix went up to $20. So now it's 40x plus 20y. And what are the combinations of that equation of different x's and y's that now give us 400? So now it becomes these combinations, and I plotted that here, and see how the budget line for pancakes shifted or kinked down from 40 to 20. And so now the total number of pancakes you can now buy is 20 boxes, and the total number of whiskey bottles you can buy didn't change, but the combinations did. So this, because of the price increase, this shifted down. You could buy less, and the new budget line becomes the intercept of 20 and 0 there, and the other intercept is the same, but the combinations that hit your budget line are different. Okay, so this one plots those new combinations where we had both the income increase of 400, but also the price increase of pancakes to $20. Okay, and there's that one. All right, then last one is based on the chapter 5 material, which is finding the profit maximizing level of labor to use to max profit in a couple examples. Okay, so let's suppose a firm produces output that can be sold at a price of $10, and the production function is Q equals K to the 1/2 L to the 1/2. So typical Cobb-Douglas production function. Part A, if capital is fixed at 1 unit in the short run, how much labor should the firm employ to maximize profits if the wage rate is 15? Okay, so again, we're trying to find this condition where the VMPL equals the W equals the wage rate, and that's exactly the point in which that's the amount of labor the firm would want to use at this condition that's going to maximize profits or minimize costs, same thing. So first, plug in your fixed value of capital. Okay, so Q as a function of capital, which is 1, and labor, which is 1, is just one of that 1/2 times L to the 1/2, and that simplifies to L to the 1/2. Okay, calculate the MPL, which is DQ/DL, and that's just 1/2 L to the minus 1/2. So here's our MPL. Now the value marginal product is the MPL times the price. So the price is $10 that was given. And we just calculated the MPL, which is 1/2 L to the minus 1/2. So 10 times 1/2 L to the minus 1/2 simplifies to 1/2 of 10, which is 5. 5L to the negative 1/2. Okay, and we want to find the point in which this equals that. So when the VMPL equals the wage rate, And we have all the information we need here. So the VMPL, we just calculated that. That is 5L to the minus 1/2, and the wage rate is 15. That was given. Okay, so what L satisfies this condition? So just do a little algebra and solve for L, and that's the amount of labor you want to use. So divide by 5, and we get L to the negative 1/2 equals 3, and multiply both sides by -2, and we get L equals 3 to the minus 2, and this is essentially 1 over 3 squared, which is 1/9. So the outcome came out a little weird here, but this is the mathematical solution where the optimal L star is 1/9. All right, so on your example, usually it should come out to a better number, but in this case it came out to 1 divided by 9. Okay, then finally, let's suppose a firm produces output sold at a price of 1, and the production function is this: 1K plus 10L squared. So if capital is fixed at 2 units in the short run, how much labor should the firm employ to maximize profits if the wage rate is $40? So same condition we want to find. Okay, first plug in your fixed level of capital, which is 2. So Q equals F of capital, which is 2L. And so 1 times 2 plus 10L squared simplifies to 2 plus 10L squared. All right, so the MPL is the partial derivative of this, or there's no other variables, but differentiate that with respect to labor, and you get, this isn't affected by labor. So 20 times 10 is 20, and then 2 minus 1 is 1, so it's 20L. Uh, the VMPL is this times the price. The price was given at 1. 1 times the MPL you just calculate is 1 times 20L, and the VMPL is just 20L. Okay, now set the VMPL equal to W to get this condition, and then solve for L. So we want the condition where the VMPL equals W. The VMPL was 20L. The wage was given at 40. And this one comes out a lot easier. Just divide both sides by 20, and the optimal L is 2 units. Okay, so that is the practice midterm and the kind of the review session there. So 4 questions. Okay, we just solved each type. So any questions on net present value, uh, the elasticity or regression problem, or the budget line analysis, or the profit maximizing problem from chapter 5? So everyone good on these types of questions, or any questions on any of these? Okay, so you have all those materials there for your reference. So here's the practice midterm we just went through with my solutions in the Word document and then the stuff I did in Excel, and that was the data set. Okay, so now let me just pull up. This is your actual midterm. There's a Word version and a PDF. They're the same exact thing. It doesn't matter which one you use. So midterm, under midterm summer 21, open up the midterm summer 2021, and here's the midterm summer 2021. Word document or PDF. I can do this one. Okay, so here's your midterm. Take home. And the instructions are here is worth 100 points. You're going to submit your answer sheet via email by meeting 6, which is in 2 weeks. So you can email it. Remember, this is so email me your answer sheet for the midterm by Monday, July 12th, just to my email address. And if you could put your answer sheet in a Word document or a PDF, that would be the preferred format. I don't really care which one. Okay, and so you got one question on net present value. You got one question on elasticity where you're going to do a regression analysis. And the data set you're going to use for this one is the midterm underscore Q2, which is right here. Okay, so for question 2, just open up this file that I have attached. Okay, here it is. And then here's your your data for natural log of Q, natural log of P, and natural log of advertising. So you use this data um, to to do the regression and answer this question. All right, so you got to take the data set, use data analysis to run a regression, and just answer the questions there. Okay, and then number 3 is on the budget line analysis. So you got another question similar to one we just did. And then the final one, you've got another question on a couple examples for the profit maximizing input usage. So stuff from chapter 1, chapter 3, chapter 4, and chapter 5. Okay, so again, this is due in 2 weeks because we don't have a meeting next week. So it's not due, and it says this on the syllabus, but it also says it here. This is due via email Monday, July 12th. And you can just, again, email me your answer sheet to my email address. Yeah. Okay. So questions at the moment on the midterm, the take-home midterm? Okay. Okay. Yeah. And so the you got your take-home midterm. And so yeah, like Valerie asked, you can if you have any questions on the midterm or anything else, you're welcome to email me, and I'll try to get back to you as quick as I can. Okay, and then also just don't forget that the homework for chapter 4 is due today, so make sure you get that in sometime today. All right, so just let me just revisit the syllabus because we're not meeting for 2 weeks, and then we'll wrap things up. We're almost done. Okay, so we're essentially done with um, the first half of the class, and normally that would have been 5 meetings, but I kind of combined things, so that's why some of the like these 2 meetings were a little bit longer and so on. So we've done half the class. All right, and as some reminders, this is due today, homework chapter 4 in the discussions. In 2 weeks, homework chapter 5 is due in the discussions. And in 2 weeks, midterm exam is due via email. And you don't have to wait till the last minute. I mean, you can email whenever you're done. You can send it to me. All right, just email it to me before um, Monday, July 12th. And then just as the syllabus notes here, and then in the meeting schedule. Okay, we're not going to meet next Monday because it's an observed holiday, and the university is supposed to be closed. So no meeting, and our next meeting won't be for 2 weeks. And don't forget to come back Monday, July 12th. Okay, so if there are no more questions, um, that's all I have, and I'll see you all in 2 weeks, Monday, July 12th. And if you have any questions on your midterm or anything else, then send me an email. But if not, I will see you in 2 weeks, and have a good rest of your 2 weeks. All right, so thank you.
Okay, thank you, teacher. Bye.
Oh, thank you. Yep.
So, teacher, I have a question. The
Yeah.
midterm, the answer we will submit your to the email.
Yeah, yeah. So you just email me your Word document or your PDF.
Okay, Word or PDF is okay.
Yeah, either one is fine. Yeah. So whatever
Okay,
like what do you when you turned in your when you're home you turned in your homeworks, did you
okay,
did you do a PDF or a Word document?
okay. Thank you. Bye. Take care.
Okay, thanks. You too.